burn 7 gallons of fuel per hour and produce 90 brake
Mine
horsepower.
downstairs
What
too.
is the thermal efficiency of the
Oh,
engine?
that one.
We're at 27%.
You round up or you feel like that's more?
Yeah.
It's a hard, that's a different, that's a hard call. I mean,
27%.
27%, give or take, whatever the rounding is, whatever, whichever way you round it. 0.27, you got the answer, right? What is the, number 9, what is the brake specific fuel consumption of an engine developing 250 horsepower, burning 15 gallons per hour with 92% mechanical efficiency? And effective power stroke overlap. Anybody have any trouble with these?
How did you get 0.4 for number 9?
Yeah.
Be around.
From 0.39.
How far back do you want to go? What did you get? Did you get something close?
Just trying to figure out what I did wrong.
Yeah, you just.
92% mechanical efficiency. What did you get for brake horsepower?
230?
Yeah, I got 230. Okay, so it's
Maybe,
just
maybe I calculated it.
Yeah.
You have the numbers right there.
So 230 brake horsepower is correct.
Oh, I did write it wrong. Sorry.
Okay. Yeah, I'm not necessarily go through this unless some judge a problem, or they want to see me after. There's some things to cover today. Okay. Next topic. So the indicated horsepower, that's what the design produces in the cylinder, just by itself. Then you have friction horsepower, so it takes some horsepower of that indicated horsepower to run the engine. You're left over with brake horsepower, and where is that? Prop shaft, crankshaft, prop shaft. Prop shaft is the better word on it because some engines have a crankshaft goes as direct drive like your light pumping, but the others have go through a reduction gear. That's not the crankshaft, that's the prop shaft. So it's best to refer to it as the prop shaft. So what makes the aircraft go forward? The prop, right?
Yeah, for us.
What does the prop give you?
For us.
And the prop is inefficient too. The prop is usually only about 90% efficient. And we're not gonna get into too much about the prop here, that's 136. We'll still have some time to think about that. So the actual propulsion force is thrust horsepower that gets you going through the air. So primarily we're gonna be concerned with going up to the brake horsepower for this class. And that's what all your engine specs you need to. You can put a number of different props on an engine, which might be more efficient than another one. Okay, so thrust horsepower gets you going through the air. Okay, there's not much more new information, but I'm gonna have a video. It's about 20 minutes long. An old VHS tape that I got. So I'm gonna play that now, and that has to do with detonation. It's a cool video, a little dramatic, made in the 70s, but still valid today. Okay. I'm gonna set that door up.
One of those army babies.
I was still at the ball at that time. I was still in the balls.
If my VHS player works.
I was still in the balls. Oh, you saw it? I was still in the balls. 1970. Were we all still in the balls?
You're probably in the
You
clay.
were
Yeah,
not-
Anybody know what the
He's probably in the
competition
air.
for VHS was in the day?
I was sitting there waiting.
8-track, that's after 8-track. What was the two battles between VHS and what else?
CD-ROM?
Laser
VHS? VHS
And what? What was the battle? Who was what was the competition?
Laser
DVDs. Oh, what?
Before that.
Laserdisc? Cable.
No. No, when VHS came out, there was a competitive version of that, but it wasn't called VHS, it was called something else.
Betamax.
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 Damn, you old.
They show you
Damn,
You
yo.
probably Googled it.
Wait, Betamax. Old soul.
Betamax.
Oh no, that was 8-tracks. Yeah.
Beta never lasts very long.
You too.
That's
You
so
guys are like, man, those
It
are
was a
good old
different thing, you
days.
could not mix the two.
That was, yeah, you had to put it in the
Oh,
adapter, right?
that's
Into the there was a VHS adapter.
I never had one, so I don't know. I just had VHS.
Okay.
I thought VHS was the greatest thing.
Okay. Yeah, VHS was.
All I know is Sarpaz.
You know what I used to serve wine.
You wish.
A drill, and then you just put it in that.
It was
Before
smaller though,
VHS,
right?
it was
The
just
Betamax?
film.
You were
Yeah, it was regular
tapes
tapes.
with a drill?
Yeah, you could rewind a cassette tape. Even tape cassettes, you remember?
Yeah, when you were upset, you would tear it apart and then when
Yeah.
you put it back
Yeah,
together.
you have to push the two messages on the flip over. Oh my goodness.
I still got my original Walkman. With a cassette tape, it was about this big.
Oh, yeah.
I still got them, I got it in the garage, it doesn't work, I don't think, but I'm debating whether to frame it.
They probably take it out of the museum now. No, because they have Nintendos and then, hey. I was museum, it's in the museum, okay?
Okay, it should work.
Must not
Oh, yeah, it was like a game, you had a game.
Yeah, the game, that was when you blew on it, to make
No,
it
did you
work.
have it in
Oh,
color or did you
yeah.
have it in black and white?
I didn't have it in black and white.
It was not even black and white actually, it was like.
Pixels, just pixelated.
Oh, just black with.
It was like, forget what it's
Green.
It was green.
Green.
It was green.
I mean, the original
The
Game Boy.
original. Game Boy? Used to go to
It
Sega.
was green.
Game Gear. It was green, but it's white.
What's the idle screen when it just starts like floating in space and you wait for it to hit the corner, yeah.
Is that Pong?
What the hell? You should have said mine.
Say you want to touch your DVD player for a while, right?
Oh, I seen that, I seen that. Yeah, yeah, the blue thing.
Yeah.
Screensaver.
But then it'll hit the corner like every 5 minutes or something. You wait for that.
Mine was dialed.
We used to go into it.
Yeah, I had to. Whenever it didn't work, you just. That's why I'm so good at it.
Little extra for
You
now.
know what that is.
And it's pixelated and everything.
Dude, it's got the lines and all.
That's called fast forward. Fast
Oh,
forward.
I'm mad.
Time lapse.
This is all about cars in the beginning, but it's actually a pretty good reciprocating engine, basic video, but the second part is where, we talk about, detonation.
Just skip chapters. There's no 4 and 6.
You can't just skip for like an hour and a half.
You can't skip to the next chapter.
That's a
Yes,
bull.
bro.
So no like
Fingers,
select,
fingers,
select, what is it?
Lane.
What is it? Select.
And then you gotta
Yeah.
rewind them again.
Yeah,
It's like a scene.
Yeah, select scene, yeah, so no, that's crazy.
This is like a microphone thing that we have.
Oh, fuck that microphone.
Or you can go back.
Nah, I'm just fucking around. I had one VHS. I did not for long.
Rewind it, yeah.
Oh, they would?
Sometimes.
Yeah.
Album video. You used to get the album video.
That's not like
Sorry.
video.
They had a little section.
No.
No? Whoa, that was fast. You're like,
Still scars you.
many times.
All the smaller ones.
All the small hole in the walls.
Those little curtains.
Oh, that's cool. Schoolhouse rock.
What I'm talking about is school.
That sucks, so you just have to pay for wow, that's crazy.
Like you could go to 7-Eleven and get like bagels.
Paying for the whole thing, I could never.
Yeah. Yeah, because a lot of it was packed. Yeah.
You have to use your imagination.
Yep.
You just go like this.
Yep.
Fold the sheet.
This
This is fire. Does it give it
This is combustion. This is combustion. And this is combustion. This is combustion in action.
Oh, no.
Combustion in action truly describes the reactions being observed. For this is internal combustion in a gasoline engine. Here, slowed to less than 1/100th actual speed, is a complex chemical process that has turned miles into minutes and has changed the face of the nation since the turn of the century. Still only partially understood, engine combustion has been the subject of extensive research for a number of years. Basic research to learn the characteristics and mechanisms of gasoline combustion reactions, both normal and abnormal. The feasibility and value of combustion chamber photography as a research tool was established by Doctors Rasweiler and Withrow of the General Motors Research Laboratories in 1930, when they made the first successful high-speed pictures of engine combustion. Later equipment consisted of a high-speed camera mounted above a single-cylinder 4-stroke cycle L-head engine, fitted with a full quartz window to permit a direct, unobstructed view of the combustion chamber. The most recent work has been done with a modern high-compression overhead valve research engine, more nearly like current automotive design. With the help of a mirror, the camera looks up through a quartz-crowned piston to view the combustion chamber from below. The optical path is shown in this drawing. To provide a basis of understanding, observe the characteristics of normal combustion. Viewed directly, the reaction appears only as a brief flash, seemingly created by an instantaneous explosion of the fuel mixture. But in slow motion, we see that normal combustion is not an instantaneous explosion, but rather a spreading, self-propagating flame. The process is similar to a grass fire. Burning occurs in a thin, moving band of flame. Each fuel particle burns instantly at the flame front, leaving only luminous, hot afterproducts in the wake. Viewing successive normal combustion reactions, we see that the flame spreads at a steady, even rate from ignition through completion of the combustion. The relationship of flame travel to piston position is indicated in degrees of crank rotation by the yellow trace at the edge of the film. It is correlated to the pressure development in the cylinder over the full 720 degrees as the piston repeats the strokes of intake, compression, expansion or power, and exhaust. Since the work-producing pressure is developed only during the power stroke, let's look more closely at the compression and combustion portion of the cycle. Ignition occurs at 16 degrees before top center, when the cylinder pressure is about 270 pounds per square inch. As the flame front starts to spread from the spark electrodes at the left, the cylinder pressure continues to rise. When the piston has reached top center, the flame front has moved across approximately a fourth of the combustion chamber area. However, only about 1/8 of the fuel charge has been consumed, because the unburned portion of the mixture has been further compressed ahead of the flame front by the rapidly rising pressure. At top center, this pressure has reached about 420 pounds per square inch. As the piston starts downward on its power stroke, the flame front continues to spread at a steady rate through the unburned fuel, and cylinder pressures continue to rise, driving the piston down. The pressure peaks at approximately 15 degrees after top center at about 620 pounds per square inch. Combustion normally is complete at 35 degrees after top center. Note that this engine requires about 50 degrees of crankshaft travel to complete combustion at this speed. It is found that the combustion process occupies almost the same number of crankshaft degrees at both higher engine speeds and lower engine speeds. Thus illustrating that the speed of the flame travel through the mixture varies with the engine speed in just about linear fashion. This apparently results from the increased mixture turbulence caused by higher intake and piston velocities as the speed increases. Ideally, combustion should all occur in a short time at maximum compression for greatest efficiency. Thus, an ideal pressure trace would look something like this. But since the pressure rise due to combustion requires a certain amount of time, we distribute the flame travel around top dead center in such a manner that it produces the maximum net work on the piston. The work done by normal combustion is best illustrated by a pressure volume diagram derived here from the pressure time diagram we have just seen. The area in this pressure volume loop is proportional to the work done on the piston by the combustion gases. This is the sound of automobile engine knock, the abnormal combustion phenomenon that wastes energy and limits engine compression ratios even with today's improved gasolines. The only change in operating conditions from the preceding photographic sequences is that the fuel octane quality has been reduced. This is the flame travel of knocking combustion. The burning process appears normal until the flame reaches a midpoint in the combustion chamber. Then the remaining fuel charge explodes almost instantaneously. Comparing the flame photographs to the pressure trace, we see that the combustion process seems normal until approximately 10 degrees after top center. Then the remaining fuel burns so quickly that even the high-speed camera cannot follow the course of the reaction. At the time of the explosion, the local pressure in the knocking region of the combustion chamber greatly exceeds the pressure in the rest of the chamber. As these pressures race to equalize, shock waves are created in the combustion chamber, setting engine parts into forced vibration of 5,000 to 6,000 cycles per second, causing the sound we know as knock. Although normal combustion required about 50 degrees of crankshaft rotation, knocking combustion was completed in about 29 degrees. The difference resulting from the explosion of the last part of the mixture, as indicated by the sharp pressure rise. The fluctuations during the expansion were caused by the reverberating pressure waves resulting from the explosion. With its sharp pressure peak much nearer top center, knocking combustion might appear from the pressure trace to be more productive of power than normal combustion. But the area under the pressure volume curve is all important. The shock waves that start engine parts vibrating and cause the knocking sound also cause rapid alternating gas motions, increasing the heat transfer to the cylinder wall. This causes rapid heat loss and thus pressure dissipation. The work lost by the additional heat energy transferred to the coolant is reflected by the shaded area of this diagram. This loss is greater than the work gained from the higher pressure peak. Knock remains a limiting factor to engine compression ratio, and thus efficiency, because it is touched off by high pressure and temperature. Under greater pressure, the fuel normally has a greater tendency to knock. Reduce that tendency, and you can raise compression ratio. Even though the mechanisms of knock are still not completely understood, it has been possible to almost double engine compression ratios. and to increase engine efficiency by nearly 50% within the last 30 years. This has been accomplished through improved engine designs and important advances in fuel chemistry. By altering the molecular arrangement of petroleum hydrocarbons to increase the gasoline's octane rating, and by the addition of anti-knock compounds, such as tetraethyl lead. But now, the anti-knock agents themselves have become obstacles to greater combustion efficiency. Although most of the fuel burns to gaseous exhaust products, there is some incomplete combustion which leaves carbon in the combustion chamber. The carbon deposits impair cooling and can cause deposit ignition problems. Some fuel additives contribute to deposit accumulation. But more important, the residual lead salts serve as catalysts to reduce the kindling temperature of carbon from its normal 1040 degrees Fahrenheit to as low as 600 degrees. With the higher temperatures that result from higher compression ratios and the partial loss of cooling, the carbon deposits can start to glow, becoming tiny spark plugs that may cause any of several types of uncontrolled deposit ignition. One result of deposit ignition is engine rumble, a random pre-ignition that is often accompanied by this sound of 600 to 1500 cycles per second. In mild cases, the phenomenon may not be heard, but would still be reflected by a loss of power and erratic engine performance. Notice that ignition occurs in the combustion chamber prior to the spark discharge in the upper left corner. An extreme result of deposit ignition is runoff, where the engine ignition system is shut off, but the engine continues to run as the fuel is ignited by hot deposits. In cases of heavy run-on, it is possible for the engine to develop sufficient power to maintain highway speeds or even climb a slight grade. Correlating the pressure traces with these photographs, we see how deposit ignition affects the engine cycle. The irregular pattern of the pressure peaks from cycle to cycle shows that control of ignition timing can be completely lost, and the variations of the pressure indicate the inefficient power development due to the extraneous ignitions. Deposit ignition problems can be partially alleviated with the addition of phosphorus compounds to gasolines to change the deposits chemically. But this method of control has less effect at higher compression ratios. The research we have seen so far has established several basic facts of abnormal and normal combustion. Normal combustion is a spreading, self-propagating flame initiated at a single point and not a sudden explosion. With knock, combustion starts normally, but the last portion of the charge explodes almost instantaneously. Except for knock, all combustion occurs in a thin band, or flame front, as the flame sweeps through the fuel. Normal flame speed is roughly proportional to engine speed. That is, the combustion process occurs within the same crank angle interval for a given fixed environment of volume, pressure, and temperature. There is an optimum distribution of flame travel about top dead center that gives maximum power and efficiency. Deposits can disrupt this optimum distribution by causing random ignitions. Although flame photographs and pressure traces have given a much better description of combustion, they have not provided a basic understanding of combustion reactions. The basic source of knock, for example, is suspected to be the complex reactions ahead of the flame front, in the dark region of the unburned gas. Since these pre-flame reactions preceding knock last only a few thousandths of a second in the engine, they are simulated in the laboratory to permit closer study and analysis. The basic equipment is a modified flat flame burner, encased in a glass cylinder covered by a stabilizing screen. The long tube extending through the center of the burner permits the addition of anti-knock and pro-knock compounds so their effect on the pre-flame reactions may be observed. These reactions are invisible in normal room light and are only faintly visible in a completely darkened room. But they can be photographed with prolonged exposures, 10 minutes for these. These are not burning flames in the usual sense, but are pre-flame reactions, or cool flames. With no additives in the fuel, it may be seen that 2 successive pre-flame reactions occur. Spectroscopic studies and other data have verified that 2 comparable pre-flame reactions occur in the engine combustion chamber. That anti-knocks do affect the cool flames is verified by these photographs. Pure fuel is used at the left, the same fuel plus tetraethyl lead at the right. The tetraethyl lead added to just the center part of the gas stream delays the reaction. That is, the reaction now occurs at a greater distance above the burner. If the pre-flame reaction can be delayed in an engine until the flame front moves normally through that portion of the mixture, then knock will be avoided. This doesn't tell us the details of how the knock reaction takes place, but it does help in understanding how to control or avoid it. Further details of how the pre-flame reactions take place are being revealed through analysis of gas samples from various points in the reaction zone. Constituents are separated chemically in a gas chromatograph, and then measured individually in a mass spectrometer. But the details of this research are another entire story. Through the continuing studies of pre-flame reactions, basic fuel chemistry, and engine flame characteristics, more is being learned of the mechanism of internal combustion. From such fundamental research comes constantly increasing knowledge and understanding of normal and abnormal combustion phenomena, and the practical realization of increased engine combustion efficiency.
The point of that was the detonation. So, you're gonna get in pre-ignition, the 2 most detrimental items in that kind of combustion.
Combustion in an engine. It happens very quickly, a few thousandths of a second from start to finish. Yet it normally is an orderly flame progression through the fuel-air mixture in the system.
Take about 5 minutes, and then I got a couple of short videos on the YouTube, something about the radio engines and rotary engines. And that's about it. I want to that's review and follow.
All the way.
Take about 5.